A solenoid is a magnetic field device which gives rise to magnetic field along the axis. This is a typical diagram. What is the diagram? This is a wire which in the form of circular loops. This is a part of a loop, cross-sectional view. A current comes out here and current enters here, which comes out and enters here. And this dot represents current, and the circular circle indicates magnetic field. Since it is a dot, current is coming out of the plane, the magnetic field is anticlockwise, here anticlockwise. When you consider with respect to this anticlockwise, consider neighboring wire, again current is coming out. If current is coming out, again it's anticlockwise. If it is anticlockwise, it looks like here. When you compare these two arrow marks, the magnetic fields are equal in magnitude and opposite in direction. Hence, magnetic field cancels each other. Means between the wires, the magnetic field nullifies each other. In the similar case, in the bottom also, the cross indicates current is entering and it is a clockwise magnetic field. Here it is a clockwise. When you compare the neighboring wire direction of a magnetic field, again magnetic fields are equal in magnitude, they cancel each other. Hence, I can say the magnetic field between the wires, between the closed wound wire, it becomes zero. Only the magnetic field persists along the axis. And solenoid is nothing but a long straight wire which is wound over a material, and this diagram depicts the magnetic field due to a solenoid. This small diagram is a cross-sectional view of a solenoid, a long solenoid, long straight. I just want to write an expression for magnetic field inside the solenoid. To obtain an expression for magnetic field inside a solenoid, as we learned, between the wires, this is again current coming out and current entering. This is a cross-sectional view. This dot, the top indicates the current is coming out of the plane. The cross indicates current is entering into the plane. And this is inside part. And the lines indicates magnetic field along the axis. This is magnetic field along the axis. It satisfies right-hand thumb rule. Current comes out, it enters. Now, to understand, let A, B, C, D be an Amperian loop. A, B, C, D, an imaginary Amperian loop. This A to B is H. Similarly, C to D is also H. As I said, outside this particular this region, there is no magnetic field. Hence, the outside magnetic field is zero. This length will not contribute C to D because the product of magnetic field and the length, this length cannot be zero. Since magnetic field is zero, this left-hand side becomes zero magnetic. Hence, there is no current included, this formula. And this all are familiar. We'll apply Ampere circuit law, this whole to the Amperian loop. We divide into AB, BC, CD, and DA. So when I write this Ampere circuit law, which is a line integral or a closed loop, this is a closed loop. This BDL, magnetic field, which is constant and along the axis. This DL is the total length of this Amperian loop. I have divided into AB plus BC plus CD plus DA. AB will contribute to this, whereas BC and DA are perpendicular to the magnetic field. Since they are perpendicular, the contribution is zero. Hence, CD will not contribute to the current, and even BC and DA will not contribute. Hence, the line integral or a closed loop DL is nothing but the length. That length is nothing but H. H is nothing but AB, the length AB, the loop length, that is Amperian loop length AB. Hence, I have replaced the line integral closed loop DL is nothing but L. L is replaced with H. On the right hand side, I stands for current enclosed. To understand what is current enclosed, let small n be the number of turns per unit length. Means you have a wire, one turn, current wire, 1 turn, 2 turn, 3 turn, 4 turn, 5 turn. I don't know what is the total number of turns. Let me say small n equal to number of turns per unit length. This capital N for number of turns. I want capital N. Current enclosed is nothing but current coming out from this wire. All the wires are supporting the same current. What is the number of turns in this small region? To calculate capital N equal to small n into L. L, as I said, this DL becomes L. In this region, H. So in this small region, how many turns are there? This N stands for number of turns in this particular region, that is A to B. Yes. When I do that, IE is replaced with I into N. This N is replaced with small n into L. Small n into L. L is replaced with H. I have already done that. Capital N equal to small nl. Capital N equal to small n instead of LH. So when I substitute, I'll end up with a small beautiful formula. B equal to mu 0 Ni. This formula is going to support you with respect to the solenoid magnetic field. Magnetic field inside a solenoid is given by B0 equal to mu0 n I. And mu0 stands for permeability of air and number of turns per unit length. I is the current which is into the wire.